everybody can hear me all right then? And then can everybody see my iPad screen? I'm writing something on there. Awesome. Okay. This will serve as our whiteboard through the semester. Okay. So we will be talking about the differential equations. Okay. Let's talk a little bit about what is differential equations. Today we will just go over the basic, right? We know what an equation is. Okay, maybe, I don't know, equals 3. We know how to solve it. Now for differential equation, basically what we have is not only we have regular variables, but we also have the derivative of a variable. For example, dy over dx equals 2y squared plus x squared. So very well, this is going to be a differential equation. And clearly the differential equation part comes from this derivative here. Okay, that's basically what differential equation is. How to understand it? Let's understand it from two different perspectives. The first one is from physics. Naturally, we need them. Why? Because physics play with quantities such as distance or displacement, deal with velocity, acceleration, potential, force, and on and on and on and on. And naturally, if you think about it, they satisfy those kind of relations such that you cannot avoid differentials because velocity is clearly the derivative of displacement. And acceleration is clearly the derivative of velocity. Okay, and the force is actually the partial derivative of potential with respect to space. So all the quantities you want to set up a relationship with, they naturally just contains derivatives. For example, it's very possible that your acceleration depends on your velocity. So they show up in the same equation. If you think about skydiving, you're going to have air resistance, which will cancel part of your gravities, right? And the basic rule is the faster you're dropping, the bigger the acceleration, the bigger the air resistance. So it's a simple relationship that is your acceleration equals a number times your velocity. Then automatically you have v times a number equals dv over dt. That is already a differential equation. Sounds good? Okay, so from the first perspective, physics requires you to do this because you kind of put all the quantities together and they have derivative relationships. A second way to think about it is from mathematics, purely mathematics. We know how to solve this. And the answer is 1. Because we define a function, fx equals x squared minus 2x plus 1, and then we ask, when will this x equal to 0? Okay. After that, we found this is awesome. Can we throw in something other than a number and try to do the same thing? Then, of course, we found something called linear algebra. I can throw in a vector. I can produce another vector. So if you think about it, it's almost like a fx equal to b. You throw in a vector, you multiply it by the matrix, you got another vector. So you solve, again, fx equal to b for x. Now when you solve this equation, your answer is going to be x is a vector. Not equal, is a vector. Good so far? Now, of course, you wonder what else can I throw in and make a function? Can I throw a shape in? For example, I can throw a sample space. Then suddenly I got some number that is called a probability. Okay, that's everything you need for probability theory and statistics. So finally, what do you want to throw in? You want to throw in a function and solve it. Okay, for example, you can throw in f, something about this function y, something about the derivative of y, something about the second derivative. You can throw in all those kind of functions you want to throw in, and then set it to be 0 and solve for y. So it's a natural generation of going from number to vector. If you're still not happy, go from vector to sample space. Not happy, put function in. Okay, so that is another way to see in mathematics. If you just push yourself through, eventually you will start to have a function of a function. Then the function naturally shows up in an equation. And when you solve it, you are not going to get a number. You're not going to get a vector. You're going to get a function. Sounds good? Let's see some examples. The very first one, projectile. A classic, easy differential equation. It comes from f equals ma. And what you're trying to do is simply, you're just trying to throw some objects, and that thing is going to follow a parabola and eventually hit something like this. Okay, so how do you do it? Well, other than your teacher told you it's going to be a parabola, you actually cannot just study this thing because this thing is already pretty complicated. So what you instead of doing is you set up an equation which you know, and then you try to solve it. And usually this is how we do it. We let x be the height. Okay. Then x prime is going to be the velocity. When I say prime, I mean dx over dt. Then dx over dt, again, which is x prime prime, is going to be the accelerations. And once we have the acceleration, we can do f equals ma. F equals ma. And if you're just throwing a projectile, your F is just going to be the gravity. Let's call it G, actually mg. Do you realize this is already a differential equation because you have a differential there, which is x prime prime? Okay. And we can solve it. It's pretty easy because all the things on the left is just a constant. Everything on the right, if you write it down, is nothing but a derivative. So you can find x prime by taking the integral, which gives you get plus a c. Now x prime prime, x is just going to be the integral of the whole thing again. There should be dt. Did I use t or x? I used a t. Okay. Then this is going to give you 1/2 gt squared plus ct plus a d, where c and d are constants. Makes sense so far for this one? That's a very straightforward one. And we can also see solving it is pretty easy. Okay, but just for this case. The final answer is going to be a constant. A function. With some constant. Therefore, in order to fix those kind of constant, we need some additional conditions, which is called the initial value, which we will talk about later. Sounds good? Cool. Let's push it and try something a little bit harder. This time, just taking the integral probably cannot solve it. Let's think about unlimited. Population grows. Okay. Now imagine you have a region. You have somebody, maybe 20 people just initially move in. Okay, maybe 200 people. Now you know they have a constant birth rate and death rate. So let's say the constant birth rate is going to be 0.2, 20%. And the death rate is going to be 10%. Let's just assume for the most simple case, they just stay constant. And we have unlimited resource, so people don't kill each other. Okay, so they just give birth and then natural die. That's it. Okay. Now my question becomes, what will the population be look like? What is the population? Population as a function of t. Do they just grow linearly, quadratically? Do they grow like a sine? Do they grow like a tangent? Probably not tangent, right? Okay. Then what we can do is we can take this y, be the population. Technically, it's yt, y as a function of t. Then y prime is going to be the changing rate of the population. Now, can you set up an equation for the changing rate, knowing that the birth rate is 0.2 and the death rate is 0.1? So several questions here. Number one, do you think the population is going to grow or decrease? Definitely grow, because bigger birth rate than death rate. Okay, so y prime should be 0.2 minus 0.1. Is that correct? Now you need to think about, what do you mean by rate? Rate is 0.2, doesn't mean that every 5 years I give birth to one child. That is 0.2 human per year. No, that's 0.2 of what I currently have. Make sense here? If it's 100 people, I'm going to give birth to 20 people. Good so far? So this is not the changing amount. This is just the changing rate. To get the people, you need to times the current population. And what is the current population? It's y itself. So y prime equals 0.2 minus 0.1 times y, which gives you this. Make sense so far? And pretty easy, right? Now think about how to solve it and find y. Let's use the old trick. You have a derivative. Let's take the derivative and take dt. Then after that, I got y. Beautiful, right? Problem though, I have this on the right. If this is dy, I know it's 0.1, 1/2 y squared. If this is t, I can also do the same thing. But now one is y, one is t. I really don't know what to do. Make sense so far? So we set up a differential equation, easy to set up. But this time solving it is not so easy because this one has a y, and this one also has a y. How much do I wish everything here is just with respect to t, then I can take the integral, but it's not happening. Okay. So how do we solve it? Do you know a function? You take the derivative. It's basically itself times a constant. Okay? Does anybody know? If you know it, just open your mic and say it.
E to the x.
E to the x, right? Great. So e to the x, if you take the derivative, let's take e to the t. If you take the derivative, it's still e to the t. That satisfies y prime equals y. Now, in order to get the point 1, we just need to put something here. Now, if you take the derivative, it's e to the point 1t, which give you y. But by changing it, it also give you point 1. So this one satisfies this differential equation. There should be a constant here. Let's not worry about it for now. Later we will put it there. Again, very easy differential equation. Solving it, this time we basically just guessed. And you know this cannot work for more complicated things. Okay? But that's what we have. From here, we believe firmly your population should grow exponentially because that thing satisfies this equation. And I think this equation is correct. Sounds good? Let's push a little further. This is unlimited growth. But in real life, you shouldn't have this. Think about it. If you put 50 people in lacrosse, they hunt, they don't go into each other. Of course, they have unlimited resources, they grow exponentially. But now if you put 50,000 people in lacrosse, which is what we have right now, we should grow slower than that because people start to compete for working jobs, resources, foods, and everything, right? Now imagine you put 5 million people in lacrosse. What's going to happen? They are going to kill each other. They are going to kill each other until they reach a certain threshold that the environment can sustain. Make sense so far? Okay, so naturally, we should not have unlimited growth. Instead, we should have a threshold, which is called the capacity of the environment. Let's call this number n, capital N. It can be 5,000. It can be 10,000, depending on the resource. We still have this y. Okay. Now, what do you know about this y? Well, number one, y should grow exponentially. When y is small. Because basically you don't hit the capacity, you don't even feel the stress from the environment, right? It's free resource, free food, free water everywhere. Number two, the growth rate becomes smaller as y increase. Say lacrosse is good for 5,000 people. If you only have 5 people here, feel free to grow. But if you are already 2,000 people here, that should still grow, but slower than when there was 5 people. If you have 4,999 person there, which means you only have 1 more room, your growth rate should stack to almost 0 because you only have 1 room. Make sense so far? So that's the assumption we have for this, which makes sense. Number 3, y prime should equal to 0 when y is exactly n. That means when you hit the capacity, you should stay there. No more. And if y is bigger than n, y prime should be less than 0. That means you put 6,000 people into 5,000 people, they should kill each other until 1,000 people die. Sadly, that is true. And of course, if you put 1 million people there, they die faster. Sounds good? That's the 4 things we want to have for the population. Now I'm going to propose a model which satisfies these 4. I'm not saying it's the right model, but at least it captures all these kind of features. That looks like y prime equals a growth rate times y times another number. What does this number do? This number does the following. Number 1, this number should be positive when y is less than n, and negative if y is bigger than n. So there should be a n minus y here. All right, and then we just divide it by n to make it a rate. And then we simplify a little bit. We have something look like this. Let's check. Number 1, when y is small, that means y over n is almost 0, right? Or roughly very small. That means this thing here is almost 1. So this one is almost like a ky, which means you grow exponentially when y is small. Okay? Number 2, as y become bigger, y over n becomes smaller. No, of course not. It becomes bigger. 1 minus y over n becomes smaller. Therefore, y prime becomes smaller. Good so far? Then, as your y go up, it becomes flatter and flatter and flatter and flatter. Because your derivative should go down. You should be concaving down. Still okay? Number 3. This is the formula. What happens when y equals n? Y prime equal to 0. It stays there. Finally, what happens when y is bigger than n? That means y over n is bigger than 1. That means 1 minus y over n is less than 0. Then your y prime is going to be less than 0. You actually decrease. So you kill each other until you reach n again. Make sense so far? Okay. This is a small adjustment to what we had for unlimited growth. Unlimited growth was actually pretty brilliant. You know, it's so simple, and we got exponential growth. But this modification looks even better. It's such an easy modification, and everything starts to make sense. It looks like this. Sounds good? Okay, question. Hannah, what's the solution? Can you guess it this time? It's hard, right? Okay, so number 1, this one is hard to solve. Before we can guess this one, I don't know how to guess. You may think it's exponential, but it's not. Okay, so number 1, hard to solve. Even though the equation is actually pretty easy, it's harder to solve. The solution is actually the famous logistic function. Of course, this is called logistic growth model. Okay. Number 2, here comes an interesting thing. even though you cannot solve it. Can you somehow try to imagine how the graph looks like, how the solution looks like? Let's just use what we just had before. It's exponential, right? And then as it goes exponential, you become slower and slower and slower and slower because you have to slow down. Still okay? At somewhere you are almost flat because your derivative equal to 0. So at here, you must be horizontal. Which force your graph has to look like this way? And you should have a horizontal asymptote here. Does that make sense here? Even though we do not know how to solve it yet, somehow we can know the trend, we can know the behavior. Moreover, I will know, number one, your population is growing. Number two, you grow slower and slower and slower. Number three, I know you do have a horizontal asymptote. That means you do not go to infinity and you don't die out either. That's not all the information, but that includes almost everything important, except for the details like what is y50. Of course, I have to solve it and try to get the number. But the trend, I know it with no problem. Sounds good? Okay, so this is the second thing you need to think about. Sometimes, even though you cannot solve it, you can still talk about the behavior. And you can imagine, in some cases, even for the most brilliant mathematician, they cannot solve a certain differential equation. But they can still talk about the behavior. Okay. In physics, of course, this makes sense, right? You care about if the energy is going to be infinity. You don't care about when. You just want to know, is it finite? Of course, it's good if I can solve it, but if I cannot, I can still talk about it. That's great. Number three, of course, this is n. And what if you start bigger than n? Like we said, you put 1 million people here and you only have room for 5,000. What's going to happen? They start high. They kill each other really fast. Okay, as they reach 6,000, they start to slow down. 5,000, and eventually they actually go like that. Okay, so we do have a logistic decay. 1k is negative. Make sense so far? That's roughly all the examples we are going to give at the beginning. We start with something really easy. You have the derivative, you just take the integral, you solve it. Okay. A second one, you can guess it. The third one, you cannot guess it anymore, but somehow you can still talk about the solutions. And if we give you a fourth one, that's probably something you cannot solve, but you can still talk about the behavior. Okay. This is the first one. This is the second one. This is the third one. Oh, yeah. What do they have in common? If you want to give them a name, how do you call them? Think about it. If you have something, just say it.
Would they be first order differential equations?
Beautiful. First order. What do you mean by order then?
So we see y prime. So like we took the first derivative. So
awesome. Yep. Can we have second order derivative? Of course. Then we're going to have second order differential equations, third order. So the first important concept of differential equation is the order. This one basically tells you how hard it is. In general, second derivative is harder than first. Third derivative is harder than second. Okay. Anything else you notice they have in common? Actually, they don't. Okay, I take it back. The second thing is called linear. Okay, it's linear basically means you have y prime, you have y. Maybe later, even if you have y prime prime, they are combined in a linear fashion. That is, you have 2 times, you have plus, and maybe you have y prime divided by 2. That's fine. But you will never have something like y prime square sine y prime over y prime prime. You will never have something like that. In those kind of cases, it's not linear. Okay? Now, easy, hard. The low orders are easy. The high orders are hard. The linears are easy. The nonlinear differential equations are next to impossible. So sadly, we have a lot of nonlinear systems, and we cannot solve them analytically. It's just difficult, very difficult. We can only solve a few. And a lot of times, what we do is we locally treat them as linear. That involves linearization. That is tangent line, tangent plane. That involves linear algebra, which means going from a vector space to another vector space. It only works for locally. Sounds good? Okay, 2 more examples, just for fun. Let's try a second order one. Spring mass system, or we can call it the harmonic oscillator. Okay. It's a classic. You got some smooth surface. Okay. You got a spring attached to the wall. You got a mass here. And this we assign to be 0 at the relaxation point. At there, you don't have any force. Now what I'm going to do is I'm going to pull this thing to the right here to stretch the spring a little bit. After that, I release my hand. What's going to happen? I am going to have a force this way pulled by the spring. So this object is going to start to move all the way up to here. Then there's no force anymore, but I still have the velocity coming from previously. Then I will keep moving to here. And gradually my velocity reduced to 0. But now I actually compress the spring. So the spring is going to push me this way. So I'm going to go back onto here, but still I have velocity, and then I keep going. So you can see this thing start to oscillate by a simple analysis. Back and forth. Sounds good? Okay. Can we set up an equation for this? Be the displacement from x equal to 0. Okay. The x prime velocity, x prime prime acceleration. Okay, then F equals ma. We already have the other side, which is m times x prime prime. We just need the force. Good so far? Now, what is the force offered by a spring if you already know the displacement or how much you stretch it? Okay. That's given by Hooke's law. Which is F equals Kx with a negative. Here K is the spring constant. Tells you how strong the spring is. Strength of the spring. Bigger the K, the stronger the force. X is the displacement, and the negative sign basically tells you if your displacement is to the right, your force is going to be the opposite. That's why it's here. Sounds good? Let's put them together. F equals ma. That is negative kx. Force equals mx prime prime. Second order differential equation. Can we solve it? K over m. What's the solution? If you know it, just say it. This is just a constant, right? What you're looking at is something like you have a function, you take it for twice, you got the negative of the function. Hannah?
Sine.
Sin x. You take the derivative. You take the derivative again. Okay? Become negative itself. So sin x. Does cosine x work? And by a quick calculation, it also works. Okay. That will be the solution. Of course, you have a constant, so you have to times something here. So if you do it for twice, it becomes k over m. Therefore, we want the square root. We also have another potential one. Okay. And maybe we have a third one. We will leave that thing again for later. But for now, both works. Okay. Everything makes sense? Pretty easy. Unnecessary because we already know it's going to shake. So of course it's a sine cosine. Okay. But now things become interesting. What if this is not smooth? Well, you still have the same thing. Ma equals f, mx prime prime equals f. Your f now has at least one part. That is going to be the spring. But now you should have another part. That part should be your friction. Does anybody know the formula of the friction, if any? Okay, physics majors, time to test your knowledge. Come on, fight for your department. Actually, fight for the education of your department. Don't know? Okay, yeah, it's proportional to your velocity. So let's just put a, I don't know, F here to indicate it's a constant times your velocity. And it should have a negative sign because if you're going to the right, your friction goes to the left. Okay. But wait a second, your velocity is nothing but just your x prime, right? So here you got the complete version of spring mass system. Okay, this time with friction. Friction. Can you guess what the solution is? Okay, it's definitely going to be not sine anymore, but it's still going to shake. But it's going to be something like that. Okay, shakes smaller and smaller and smaller because you lose energy. Okay, how to write down a formula for that? We will show later. This is a classic system, so we definitely is going to solve it. By the way, this is also the differential equation for electric circuits. Happily, they share the same format. Okay, so we can solve them together. Okay. Sounds good? That's the second order derivative, second order differential equations. Okay. I think that's enough introductions. Do you guys have a rough idea about what the differential equation is now? Okay, and can you see why that thing is important in real life? Because usually the equation is pretty easy to set up. You just play with force, acceleration, and things like that, ignoring they have underlying connections, which is one is the derivative of the other. The difficulty then is just once you set up the equation, solving it can be tricky. Okay. Now, of course, how do we solve differential equations? I already give you some hint. The first one is you just solve it by calculating. So using math, we call it analytical. It's half guessing, half experiences. And of course, if you're so brilliant, maybe you can solve something that nobody can solve before, but then everybody after you will be, again, reading your work and then become using experiences. Okay, that's usually what we call a breakthrough. In general, this only works for typical. I won't say easy, but typical ones. Okay, we only know how to solve some of them. The rest will be, we cannot solve it. But then we talk about behaviors without solving. Some things we can talk about, including something called asymptotes, or we call it equilibrium, which is basically what happens as t goes to infinity. We also talk about some special points, not the whole solution, but some special value. That usually happens when y prime equal to 0. That means that's where your function stops changing. Maybe your function will stay there. Maybe it will kick off again. Okay. Number 3, we don't have a solution and we don't know how to talk about it. The third thing is always numerical solution, which means solve it by computer. It's great. You can solve anything using this. And of course, there are some problems. The major problems are your solution is going to be some curve, and that curve is going to be continuous. But when you use a computer to solve those kind of things, you have to because computer can only represent finite numbers. You have to cut them into small pieces. To make your solution better, you just take more points. So what happens is your computer is going to take a discrete approach. Now the problem becomes, if you take as many points as you can in the discrete approach, will that thing eventually converge to the real one, which is continuous? And the answer is definitely no. There's no guarantee. You need to verify that. So it's very possible you solve it with a computer that the solution is ridiculous. The sad thing is you don't even know. Okay. The second thing is, even if eventually the algorithm converges to the real one, does it converge in reasonable time? For example, if you take 1,000,000 points, you can have the right solution according to your analysis. But that takes 2,000 years for our computer. That's still not tractable. Make sense so far? Okay, so actually this is the whole area on how to construct numerical solutions of differential equations. It's not as easy as just plug in the computer and do it. It's very complicated. Of course, for the easy ones, they're easy. Okay. Now let me show you what we have for what we did before. Let me share. Oh, before I go ahead and show you the examples, any questions so far? Good. Now let's share my screen. Can everybody see my screen right now? Okay. The problem is I forgot where I put my code. Let's see. Okay, here it is. Okay, this is the first example we had. Okay, dy over dt equals ky. That's the unlimited exponential growth. Now what we do is we just put it into Python. I will share with you this code, by the way, so you can code it yourself. What we do is we set up a k. Let's set it up to be 0.1, so you know that thing is going to grow. We start with 200 points, and we take 10 points to discretize it. We solve it. Okay, that gives us the exponential approximation. Now, if you want to try something with a negative decrease, which means your population is going to decay, just put it in. Okay, you got something which is decaying. So computer is pretty nice. Maybe there are some errors because you only take a few points. What you can do is you can actually increase the number of points. And of course, your graph just becomes smoother. Usually, the more points you take, the better the results. Okay, later, we will have a section to talk about how much you need. Now, here's the second thing. dy over dt equals k times, that's the logistic growth. Let's set the capacity to be 1,000. Let's start with 200 people, and let's grow at a rate of 0.3. Let's take 50 points. That's what we got. Now with the same thing, let's change the increasing rate to be 0.1. You can see eventually this one should still reach 1,000. This time just slower because you have a slower growth rate. Still okay? Now let's change this one back to 0.3. We have something here. We start from 200, we end at 1,000. Let's change the capacity of the environment to be 3,000. Now you can see this one can, suddenly you remove the cap, they keep increasing after they hit 1,000, but eventually they actually top at 3,000. Sounds good? Of course, let's try the case where people kill each other. So let's try 20,000. Start, we have a 3,000 left. We have a decay, 0.3 growth rate. You can see actually when people kill each other, it's pretty efficient at first. Okay, it probably take you, I don't know, 3 years, 4 years to kill more than half the population. Yeah, so that's what we got for this one. Spring mass, the same thing, negative K over M, you solve it, you got this solution here. Okay, the orange one is actually the velocity. I put both of them there. Now, what will happen if you make your spring stronger? Which means you change your spring constant from 0.1 to 0.5. They just oscillate faster. Okay. What if you change that thing to be a heavy project? It's 1. Let's change it to be 10. 10 is probably too much. Change it to be 8. Okay. You can see that thing actually smooths down again. Kind of makes sense here. So now if you go back to your solution, suppose you can solve it. It's square root of K over M, which tells you how fast that thing is oscillating. That means a bigger K or a smaller M will both give you a faster frequency. That makes sense. And the beautiful about this simulation is, seems like when you want to know what happens to something, if you can set up the differential equation, you don't actually have to do the experiment. You can just do it in your computer, which is cheaper and faster. Sounds good? Finally, there is an example we didn't go over. I found it, yeah, I don't know. Try to read it yourself. Predator and prey. You have 2 things. The first one is called the rabbit. The second one is called the fox. Okay. The first one is going to grow at a rate of alpha. The second one is going to die at a natural rate if there's no food, which means if there's no rabbits. Good so far? Okay. Now here's the interaction term. If there are fox, then when the rabbit have a natural growth, they are going to be captured and eaten by the fox. Therefore, there's a negative times the ratio. The bigger the population of the rabbit, the bigger the population of the fox, the easier for them to catch it, not for them to catch each other, for the fox to catch the rabbit. Similarly, we have something here. That is, if we have food, the fox can actually stop dying. Quite simple. We put them together. We got something like this. The blue is the rabbit. The orange is actually the fox. What happens is, at first, the rabbit grow because there are so few fox. And when they have a threshold, maybe we have 2 fox left from last generation. They start to eat rabbit and reproduce. After a while, they start to hit. They start to reproduce themselves. But then you have too many foxes. Now the rabbit is going to suffer. Okay, until there are not enough rabbit, then the fox population goes down, and you do this periodically. That is a good model. Now think about it. If you play with the birth rate and death rate, and also the capture rate, can you possibly create a case where they just die out and they never bump up again? Okay, that is what you can do by manipulating a differential equation to predict what's going to happen in the future. Okay, that's exactly how people do it to save the species which is close to extinction. How much do you need to capture? Or how much do you need to actually throw there so that they can, like the wolves in Yellowstone, so they can reproduce themselves at a faster rate so they can survive. Okay, that's all for today. I will share the screen. No, I will share the video online and also the notes, so feel free to check them. Feel free to leave, and I will be here for questions if you have any. Andrew.
I was looking on the web work, and it said that the due date for 1.1 is 6/10/20, so in June.
Okay, so then don't worry about it. I haven't opened it yet. I will
Okay.
reset the due date to be on next Saturday.
Awesome.
Yeah.
Thank you.
Anything else? Yeah, feel free to leave if you don't have questions. I will just stay because some people may have questions.